Now in this video we're going to talk about a specific example of simple mathematical models. This is modelling diseases, the spread of diseases. This is very topical at the moment because we've all recently come out of a COVID pandemic. And it turns out that a remarkably large number of the people who actually do modelling in, say, the COVID pandemic are actually physicists by training. They're not biologists. That particular expertise that physicists have of coming up with models, mathematics, is enormously valuable. And in fact, John McCaw, who did much of the modelling for the Australian government, is a physicist by training, and I've borrowed many of these slides from him. So let's look at the simplest possible model of disease spread. This is called the SIR model, and most of the more complicated models are based around this. So we're going to divide the population into susceptible people, infectious people, and people who are recovered. So susceptible is anybody who could be infected. Infectious people are the people who currently have the disease but are still walking around and infecting other people. And then recovered are those who've had the disease, have recovered or possibly died, and therefore are no longer susceptible because they're now immune, and they're no longer infectious because they no longer have the disease. Okay, gross oversimplification, but that'll do for the moment. Now here are the assumptions we're going to make. Remember, every model has assumptions because the real world is insanely complicated, and unless you make assumptions you can't write down simple models. Now what we're going to assume here is that every infectious person will infect a certain number of others, R naught. This is not going to be everyone they come into contact with. There's going to be some fraction of that, but that doesn't matter for the moment. We'll just assume that every infectious person, say, infects 5 other people or 3. This is the R naught parameter we'll talk about in a moment. By infect I mean expose the other people. If these other people are immune because they've already had the disease, even though they've been exposed, they won't catch it. But we're assuming that of this R naught, everyone who has not had the disease before will catch it. So of course, it's not everyone they've been in contact with. They won't infect everybody. And then we're going to assume that some fraction of the infected people recover and some die, and either way they stop infecting other people. A dead person's not going to infect other people normally, except maybe the pathologist. So now we can write down some equations. So here we've got di by dt, so the rate of change of the number of infectious people. And this is going to depend on beta, which is the transmission rate, so that's how infectious it is, times the number of susceptible people. So clearly you're going to infect more other people if there are more people out there who are susceptible, i.e. don't have immunity, whereas if everyone has immunity you're not going to affect other people. Times I is the number of infectious people out there. You're more likely to catch the disease if there are more infectious people walking around. So if there's 1 million people currently infected walking around, that's 1 million times more likely to infect you than if there's only one, divided by the total population. So that's the infection rate minus the recovery rate. So that's the number of infected people times the chance that any person will recover one way or the other. The number of recovered people by time is just the recovery rate times the number of infected people. And the number of susceptible people is just going down by this term because as more and more people get infected, there are going to be less and less susceptible people. And R naught is beta over gamma. It's the transmission rate over the recovery rate. And if this is larger than 1, you get exponential growth. So very simple model. What does it predict? Well, here's the cumulative number of infections. It shows a sigmoid shape. It climbs and then flattens out. So begin with very few people are infected. It grows exponentially until, like most of the population, are infected. Then it flattens out when almost everyone has been infected. And the infection rate shows a peak. So the maximum rate of infections will be when lots of people are infected and spreading it, but still most people are not immune. And this makes clear predictions. It says that it'll grow exponentially, and exponential growth is something that most politicians don't understand very well. If something doubles every week or every 2 weeks, you've got to get in very early to do anything about it, because by the time it's started doubling a few times, it gets very, very large. And indeed, here are the number of coronavirus cases in Italy and the US between February and March 2020, and they're growing exponentially, as you can kind of see if you look on a log scale. So indeed, this very simple model works quite well in the early stages. It does say there's exponential growth, which is really scary. Over the longer term, however, it doesn't quite look like that. This is the number of cases in South Africa over a period in 2022, and you can see it climbs exponentially, then drops, then climbs exponentially, then drops, then climbs exponentially, then drops. You get a whole series of waves. So this is an example where the simple model doesn't work. And you can add complexity to the model. You can, for example, say that your immunity goes away. So maybe you're only immune for 6 months after you have the disease. And a model like that doesn't indeed give a series of waves, because what's happening is everyone catches the disease, then their immunity wears off, then they catch it again, then it wears off, and then it catches it again. Or it could be that there are new variants of the disease coming along that evade the immunity, which also has a similar sort of effect. So you get like the Gamma and the Omicron versions of COVID that came through and could evade the immunity caused by previous infections to some extent. So this is an example of a simple model which actually tells you quite a bit.